So the YouTube is always the one that is causing these problems. I don't think it is a YouTube actually at all because, but there is this hybrid thing that kills everything. Because I'm this Lex room. No, it's okay. It's okay. Yeah, but not for laptops. For laptops, really. Okay, so we are online. So can you double check that we are good? Are we okay? So far, so good. This is it. Okay, okay. Are we good? We're good. Finally, we're good. And streaming is healthy. How is the quality of the streaming? Okay, you cannot get all in your life. Oh my God. Hey guys, it's not going to be perfect today. So we're going to have a short lecture today, and I'm going to make a longer one next week because this computer is simply not willing to cooperate. It's not going to be possible today to make anything better than what it is. So recording will be not beautiful. Okay, but hey, can we get started in a way that I have an announcement that I would like to make? Today is Aki's name day. To celebrate that, I got few candies to you guys. So which one? You can switch if you don't like this one. And I want to see this to camera. So this is what you're missing if you're not coming to my lectures. Ah, and then Mustafa is my, I'm going to owe you the one. It's a name day. It's like Patrick's Day, Saint Patrick's Day, and Saint Aki's Day. Is it? Also, there's another important day today. Today, the day and the night are equal in length. Yes, today is the day. Today is the day. So we are approaching the time that the daylight is become to be much longer than the night. That's a fantastic. That's a fantastic. The next 6 months is going to be like great. Too much energy. Yeah, because you don't know what is that we're gonna celebrate next time. So thank you very much for being here. And those ones that are underway to come this place, you're gonna be just simply too late. The candies are already divided. Good. All right. So like I say, hey, see you. It's gonna be short today. I'm thinking like we're gonna close roughly at 11:30. Yeah, because I don't want to have this material that the way it is recorded is it's just simply not good. Simply not good. All right. So like you noticed, we are facing technical difficulties today. Some kind of the update in my computer, which make it is impossible to display the screen well. So only participants are not going to see me in a full screen, but is it like 1/4 of the screen or something like that? And that's not going to be possible to change today. That's why we're going to have a somewhat short meeting today, lecture today, and we're going to continue to discuss about other details on Wednesday. Few more highlights that I would like to give it to you. And today, I would like to close this discussion about modal reduction and how that can be used in the floating frame reference formulation. And today you're going to learn where this floating term is coming from. So what that is standing for, the floating, and how how it can be sometimes floating and sometimes not. That I would like to explain to you. And another drawback that we have, technical drawback, is that I'm not able to do the drawings to my laptop. So I need to do the drawings to the whiteboard. and we'll see how visible it is. But anyways, so that's what we're gonna do. And then actual good reason to model flexible bodies is that then you have this ability to monitor the strains and stresses. Strains usually are not that interesting, so people are not interested about the strains, but stresses they are. And once you have flexible body, then you have an opportunity to monitor the stress histories. Stress history in turn is something that is very useful, particularly when you do fatigue analysis. And when you wanted to monitor the stress history in a longer perspective, you can run things in real time. You can ask an operators, the actual operators, to run your machine. And this is the way you can monitor the stress histories without having the real prototype. And it's quite the good advantage because the alternative for getting stress history is making measurements by using an actual prototype. Not easy because strain can be measured by using strain gauge. You know that? Strain gauges are something that they don't survive well in real environment. You can use it in a laboratory environment, but in real environment, they usually, if they got any physical contact, they can also get the damaged. And when they get damaged, they don't work anymore. The strain gauge is like roughly the size of my fingernail, smaller than that, and you just glue that in the surface of the whatever structure you wanted to measure, and based on the deformation of the structure, it's capable to record it, and it's very sensitive for that. Of course, it needs amplifications and everything, but the sensor itself needs to be in the surface of the structure. Now, this is hard to protect from the physical contacts, and because it's small in a size, and because it's a very delicate sensor, any kind of the physical context will probably destroy it. So that's why I don't remember to seeing this kind of the strain gauge, real like stress history measurements in actual production machines. I have seen it in the prototypes, but not in the real structures. But saying that, also good to keep in mind that strain gauge and this technology based on the strain gauge is used in most of the force sensors. So if you think about the force sensors, even the sensor that is measuring the pressure, there's a plate surface where the hydraulic pressure is imposed to. And when the plate is deforming, you are able to record the strain by using strain gauges. And other force sensors, those two are based on strain gauges. Also, the ones that are power measurements, like if you are enthusiastic in cycling, you might have this power sensor in your bicycle. That too is based on the strain gauge, and of course, on other sensors too. But that's the way it goes. Strain gauge. All right. But I don't want to explain that, but I would like to explain an alternative, which is how to use a multi-body system dynamics to get the stress histories. But prior to that, let's move on. Oh yeah, so it's going to be a little bit unpleasant because no way to highlight anything in my screen because my screen here is completely empty. All right. Core of model reduction is to move from nodal space to modal space. This is what it is. What it means. It means that we need to start looking at the structure that we're modeling by using finite element method as a structure as a whole. And then what we're going to do is that we're going to look at the certain properties of the structure, just like what are the ways that structure can deform. Now, these ways are something that we're going to use as a model basis. This will be the one that we know that it can deform in this way. How much? This is going to be something that is called modal coordinate, which is an amplification of certain deformation way. What we're going to do is that we're going to simply move from these points, which is a nodal space, to entire deformation modes. And using these amplifications, we can reduce the size. Of course, every single reduction method, we're always losing certain amount of accuracy as well, as is the case of modal space as well. But this is better than reducing the size of the original finite element model, because remember, in the finite element model, you need to make sure that the model is converged, meaning that it is having enough degrees of freedom that it can predict deformation accurately. This is something that we must have. Now we can reproduce accurate deformation if we properly select these modes. And that's why the compromise we do for model accuracy is not necessarily that significant. But always remember, every single reduction technique is always introducing the loss of accuracy as well. And they also introducing the enhanced computational efficiency. So that's a trait. So we get better efficiency in a computing, we lose a little bit of accuracy. And you just need to make sure that you somewhere in the balance. Make sure that computational efficiency is as high as possible. The accuracy is a damage you can introduce. The accuracy is not overly significant. Unclear language. Overly significant. What's overly significant? This is case dependent. And that's why I cannot give any other rules than these unclear rules. All right. So what we do then is that we're moving from not a decrease of freedom to moderate decrease of freedom. And that what is doing the mapping is this deformation mode. And now what you can see here, this is a matrix here. This one here, C, is a matrix that includes numerical values, the way the structure can deform. And it have equal amount of columns that the number of possible deformation modes. Each of the deformation modes are multiplied by unknown, an amplification factor that here is called P. Now, if this possible deformation mode is selected based on eigenvalue analysis, then the deformation modes are orthogonal, meaning that they are not dependent on each other. They are completely independent. That introduces another significant benefit for us, and that's something that when you're reducing the size, you're also getting rid of the components that are coupling the different degrees of freedom together. And as a consequence of that, your new mass matrix and your new stiffness matrix are diagonal in the shape, only the diagonal components. And you know the diagonal component is such that you can select any degrees of freedom you want, solve it, knowing nothing about others. So that's the beauty. That's the beauty. This holds only if your modes are orthogonal. Only in that case. All right. So the common way, or the one way to solve these possible deformation modes is conduct an eigenvalue analysis. And as a result of eigenvalue analysis, we can get the two set of results. First set is eigenvalues. This is a natural frequency, which is typical for the structure that you're looking for. So each of the structures, they have a certain number of eigenvalues. Actually, in the real structures, there's an infinite number of eigenvalues. There's an infinite ways that the structure can deform. Because remember, mathematically, a structure like this beam here consists of infinite number of particles. Each of the particles in flexible bodies could move their own way. So there's an infinite number of ways that this can deform. Not possible to capture by using computer simulation because we need to do something that is called discretization. Reducing this infinite number of possible deformation of ways and particles to be something that is more reasonable for computer simulation. Okay, so we get these eigenvalues, and another set of results is eigenvectors. Eigenvectors are the way the structure can deform, and nothing but the way. They have nothing to do with the absolute values. And it makes me sad to hear every now and then that somebody's making interpretation that this is how the eigenvector look like, and making conclusions about absolute deformations based on that, because that's not the case. That's not the case. All right, eigenvalue analysis. The first thing to understand is that you set your forces to be equal to 0, meaning that you have not even enough information to do any conclusions about the absolute deformations because the forces are missing here. So this is all about the structural properties. All right, so we know that the eigenvalue analysis, there is a solution for that. And once you substitute the solution, first you can solve the eigenvalues and then eigenvectors one at a time once you have this information. So last week we looked at this example spring system consisting of, or excuse me, 3 elements, and how we can conduct an eigenvalue. This, by the way, is not the way that eigenvalue is solved, because it's more, this is computationally overly inefficient. We are not able to compute the determinants of the structure that consist of 100,000 degrees of freedom. That's not going to be possible with the existing computer power. Anyways, so as a demonstration, so we're solving the determinant. We get polynomial with a fourth order polynomial, and it crosses the 0 in 4 different places. These places are our eigenvalues. These eigenvalues have a numerical value 0, 12, 60, and 120. 0 stands for rigid body motion. No deformation, but it moves as a rigid body. All right? And then one at a time, we can substitute the eigenvalues and we can figure out how is the eigenvector. This is the way the structure can deform. And here are the 2 examples. The one that is associated to second eigenvalue, the another one that is associated to fourth eigenvalue. All right, that's what we learned last time. Also, we learned this interesting thing that what matters end of the day is shape of the deformation. Shape of the deformation. And that's why when I have an example about the connection rod here, I can get the equal responses when I use 2 different boundary conditions. So the boundary condition in a finite element method means how it is attached to ground, if it is attached to ground. And first option to compute this eigenvalue analysis is to have no boundary condition whatsoever. And this is important to understand because in this particular case, the body reference coordinate system, which is the coordinate system that it is in a method A, is detached to material point, is actually floating with body. And this is what the floating is standing for. So the reference coordinate is moving along with the body, translating along with the body, but as soon as there is a deformation, it becomes to be detached from the material point. Because you see that deformation, when I have this free boundary condition, this coordinate system that is standing is typically mentioned as a global coordinate system in a finite element method. It is detached from the material point. And that's where the floating frame of reference formulation is coming from. This possibility that is floating. It's not necessarily floating in all the other boundary condition possibilities, but because of in free boundary condition, it is floating. That's where the name is coming from. So now, if I would ask where the name floating is coming in a floating frame reference formulation, you know the answer. Answer is that reference coordinate system is not attached to material point, and it is unattached in a case of deformation. In case of undeformed translation, undeformed rotation, it is fully attached. But as soon as the deformation comes in a play, it is detached. So how you think it's going to be the success rate in a shortly coming in-class quiz? 85. And I'm seriously going to ask where the name floating is coming in the floating frame reference formulas. Okay. All right. But one more thing we looked at a week ago, 2 weeks back, was the thing that, you know, in the floating frame reference formulation, there is a what it is possible that each of these boundary conditions will give you approximately the same response. It's simply because what matters in dynamics is a global motion, the motion with respect to global coordinate system. And now you can have a different roads to your final destination. And each of these reference coordinates and reference conditions are representing the different roads. But end of the day, you're going somewhere along your beam, and regardless how you do this, you will get roughly the same answer. Okay, I'm not going to put the circuit on because of the technical difficulties that I'm experiencing today, but I'm going to put it momentarily. Okay, so again, I'm not able to do the drawings here. So Now it came back. Is it just that my computer is super slow today? Extend? No, duplicate. Yeah, I'm back. I actually can see something in my screen. So it's no longer completely black. Yeah, I want to do how we. Mhm. So we're gonna keep it this way. But now how can I get rid of this window? But clicking is not willing to disappear. Yep, it disappeared. Uh, all right, I'm gonna put this on momentarily. So I'm asking what the floating means in the floating frame reference formulation. It means that the formulation is still under development. Titus? Okay, it means that the body inertia can fluctuate. Body inertia can fluctuate. Okay, it means that the strain within the flexible body can be defined easily. It means that the body reference coordinate system can move from a material point of a body. All right, clear. All right, so we'll get back to this because I'm too scared to go off of my presentation because today is not a good computer day. You know that there's a today is not a good hair day. Today is not a good computer day. Today is not a good Teams day. All that can happen in your life. Good. All right. Now, so we look at this connection rod. This case here. This connection rod happened to be an happy incident. And here, it actually doesn't really matter how you do the deformation because of the simplicity of the problem. But in real life, is not necessarily the case. I would say that it will be a lucky incident if it is a case in the real life. And setting the boundary condition to compute the eigenvalues is actually a major challenge. It is very difficult. And to do that correctly, it's pure luck if you can do that in the general case. And to solve this problem, to make the life of the users that are using the floating frame reference formulation in real life, there's a technique that is commonly approved to be efficient, which is the method that is under debate. There are cases that this method is failing as well, but as a generally speaking, this is the one of the method that is very often used. The method is called Craig-Bumpton method. And the method is all about how to set your boundary condition, how to set your finite element model such that you can get what you're looking for. And again, what you're looking for are the deformation ways, deformation modes. And like we learned, we can do this by putting the structure with floating, floating in a space. We can use the different kind of the boundary conditions, but in general case, it's hard to make this correctly. So this method should ensure that you can do it correctly regardless of the case. It goes in a way that it divides your structure to two categories, or not structure, but the non degrees of freedom to two different categories. The one that are called boundary modes, and the boundary modes are something that they are point of interest. That would be the good interpretation for that. And point of interest means that, let me see if I can do the drawings today. Not this one. This one. It's getting better. It's getting much better. So look at this. So it's Aki's name day, and the computer is starting to cooperate with me. How is, by the way, the streaming? Is that healthy? Is it looking better now? No, it's not opening. Okay. Okay. Anyways, so what I'm doing here as a beginning of my method, which is called Craig-Bumpton method. This is the one. So this is called Craig-Bumpton method. And again, the way to define the deformation of the structure. So I'm selecting some of the degrees of freedom to be called as a boundary degrees of freedom. Typically, you're selecting all the degrees of freedom in a one nodal location to be your boundary degrees of freedom. So let's say that if I have ANM, okay, so I got the problem. So it's nothing in YouTube. Really? So it's completely empty. Yeah, it's completely empty. This one. Yeah. Okay, this one. Guys, I yeah, I know this is against your recommendation. But is it back in the YouTube? All right. Okay, that's okay. That's okay because I'm not back because I'm not standing here. I think that's the reason. All right. Anyway, so what I'm gonna do here is that I'm selecting my Nora degrees of freedom to two different categories. The one that are points that I'm interested in. The point that I may be interested in are the ones that are connecting my flexible body to neighboring bodies. Or alternatively, I might be interested in a certain location where I know that there is a high density of forces. Let's say that I know that this structure is loaded in this particular node that is here in the middle, and there is a point force imposed to this point. So this probably would make sense to select as a boundary degrees of freedom. All right. So how it works in a commercial finite element software is that you're clicking the nodes and saying each of the degrees of freedom in this nodal location will be relocated to a new category, which is called boundary degrees of freedom. And the rest, what is left, will be called internal degrees of freedom. All right, that's what the commercial finite element software will understand. And based on this selection, it started to reorganize the mass and the stiffness matrix. And it reorganized the columns and rows of the stiffness matrix such that the boundary degrees of freedom appears to be in the upper left corner of the both of the matrices. So this reorganization is always possible. So we are introducing no difference in the model, except we just reorganize that unknowns. All right. So here is my boundary degrees of freedoms. And these are the possible forces that I introduced at those particular locations. What happens next is that using this categorization, I'm computing two different set of deformation modes. First set is something that is eigenvalues that are related to internal degrees of freedom. So whatever is left out from this selection will be called internal degrees of freedom. So I'm going to take this part of my reorganized mass and the stiffness, and I'm going to conduct a eigenvalue on this. Okay, so I will get the eigenvalues and more importantly, eigenvectors that are associated to my internal degrees of freedom. Okay, so that's my first set. I'm going to visualize that momentarily, but it looks saying that you attached these boundary degrees of freedom to ground. You let others to vibrate as they want, and that's going to be your first set of deformations. Then there's going to be another set of deformation, which is static deformation. You take your stiffness matrix only, and you compute internal modes, which is called static correction modes, based on the reorganized stiffness matrix. This is going to be equivalent that introducing unit displacement to each of the boundary degrees of freedom. So let me highlight this. So it's going to look like this. This is my static correction modes. These are my the one that I got from eigenvalue analysis, and they look like this. This is a beam structure, and in a beam structure, I have selected the nodes that are in both ends and the one in the middle as my boundary degrees of freedom. Those are my selection. There are many others that are not selected as a boundary degrees of freedom, and because of that, they will be called as an internal degrees of freedom. Okay, so I'm computing my first set of deformation by setting these points to be attached to ground. And what you're going to get is a deformations like this. Okay, sorry, not the great drawing, but something that there's no deformation in this point, and this point, but others are vibrating. This is my first set. Second set is that each of the boundary degrees of freedom, I'm introducing the unit displacement one at a time. So again, I have here the structure. I'm attaching this one. I'm attaching this one. And I'm introducing unit displacement to this direction, to this location, this direction, rotation. And it's going to give you another ways of deformation. This is it. This is something that takes different kind of joint connections, the neighboring bodies into account. And it also gives you the good idea to how to compute the forces if there is a force concentration in one of the locations. Okay, so that's it. So it's ready. There is a beauty mistake here. Not significant. Many people stop it here. They are happy with this selection. But the problem is that if you look at these deformation modes, if you look at these columns here, the columns are not entirely orthogonal because some of the deformation is based on statics, not eigenvalues, but statics. So they are, when you take this one here, which is called G, what is this C? What is this again? C, G. And you multiply this, your mass matrix, and your, here's a transpose, and your stiffness matrix, the end result is not going to be diagonal, simply because of this set is not orthogonal. Is that a serious problem? Not necessarily, but some people feel that it is a serious problem and need to be fixed. And you can fix this by computing uh, a new mass and stiffness using this setting, and then conducting another eigenvalue analysis. This is called orthonormalization, meaning that you're forcing each of the modes to be orthogonal. I don't know if it's really necessary, but it goes like this. You take whatever you got from the previous slide, you multiply by your original mass and stiffness with these matrices. And then you take these new matrices, which is reduced by size already significantly. You conduct another eigenvalue analysis. This goes here, goes here. And now you're going to get the deformation modes that are for sure are orthogonal. Okay, so that's how it goes in the entire story. But it's okay to live in a half the story too. It's okay too, because I feel, okay, so yeah, when I'm changing the slides, it's not changing my slides. How come it's not changing? What slides we're looking? Can you take a look at how is it YouTube? Yeah. What? Hmm. Okay, so why not? This is a weird problem. Extended and then display the extended one. Okay. So it's extended, and then I'm gonna put this screen. So I'm gonna use a window capture, and then in this whole screen display. But this is so weird because if you come and take a look at my screen, this is looking so weird. Because I have this one here. This is like a screen in this one. Yeah, yeah, of course, of course. You can double click that. These are the choices. No, it's not willing to do it today. because this was the problem in the beginning. Yeah, we can, but this should be transparent, so it's not making much of a difference. Uh, okay, that disappeared. So then if I use display, this, yeah, yeah, here. This one. Yeah, there. Like this one. Can I? Yeah. Can you? And then we say this one. Yeah. Yeah, it's going to be one quarter of the screen, but that's simply because of the. Is it? So how is it? But there's nothing we can do for that today. Nothing we can do for that because uh like somebody's it's almost looking that somebody's using my computer. Yeah, but there because there's some kind of update because you notice that like somebody opened the window. It's like somebody's using my computer. Seriously. They I think IT can use it if they want, but I don't know. Yeah. Okay. All right. So let's close the story. So this is a summary. So again, so you first selecting your not a decrease of freedom to go into two different categories, boundary decrease of freedom and internal decrease of freedom. Then you conducting a naked value analysis for internal decrease of freedom, leaving rest to fix to ground. Then you can introduce static correction modes, which are you can get by introducing unit displacement to boundary decrease of freedom one at a time. This combination would be okay, but the beauty mistake related to static correction is that they're not orthogonal. Do you remember something significant? Alexander. Hmm. Ah, okay, okay. So it's because of the visiting lecture. So how can I do that? Yeah, because it's gonna take we're gonna take the focus is going incorrect. Okay, all right. So then we can do this author normalization, and as a result of author normalization, we can actually affect all the modes because we force in some of them to be orthogonal. The consequence is that the modes that used to be the one that are coming from this fixed interface normal folds are now roughly free deformation mode. And then there is something that is introducing very local deformations, which is the boundary modes. But now you're good to go. And now you have a completely orthogonal modes. So that's how it works. And now, is it switching my slides? Yeah. So it is doing something. Yeah, okay, but why is switching? Okay, so how to do this selection then? So once you conduct the whole thing, of course, the most important selection criteria is your not your common sense, but your engineering sense. So if you see that this makes sense, then it makes sense. And if you see that is a deformation modes that are in the direction that there is no force is imposed to this direction, forget about it. So Of course, there is this possibility that you can use an automated selection, and I'm going to explain momentarily how this automated selection goes. But you just animate the deformation mode, and based on the way it appears visually, you do your selection. That's the most common way. And these are the examples. I'm going to introduce these boundary modes and the free modes to you. So the free modes are looking like this. Is this still okay in YouTube? I guess it is. So these are the free modes. You see that this is one of the low frequencies in a free modes, but the deformation is in a transverse direction, so probably not very important for us. Okay, this is another deformation, but again in a line of the loading, so probably something we need to keep in a play. So these are the deformation modes, and these are the free modes. These are the boundary degrees of freedom. You see that some of the boundary degrees of freedom are not making any sense, like the one we looked at earlier. And also take a look at the frequency, extremely high frequency. You have no chances to compute anything in this high frequency because if you really want to capture this, you should be able to use a time step that is extremely slow, extremely small, extremely small. So most of the boundary degrees of freedom are something that you need to be careful with them. You probably not need all of them. Some of them you might, but some of them are just introducing the overly high frequencies to your system. So it's still not sharing. Okay, so if I do this one, this one. Ah, what a big pain. Yeah, here. I don't know. I don't see how is OBS. Is it making any sense? Okay. Okay, what a major disappointment. I'm every now and then I'm thinking that should I leave the YouTube streaming, but I'm a little bit reluctant to do so because YouTube is with all these technical difficulties, it's still a really nice tool to watch the lectures afterwards because the subtitles and everything. I don't know if you guys put the subtitles on. Every single time if I'm checking how was my recording, I put the subtitles on, and amazingly enough, it is able to understand my English completely. I mean, there here and there is it goes incorrectly, but most of the cases is correct, absolutely correct. And that's weird because of the accent and everything. Yeah, but still, accent and everything still is capable to write it correctly. That's weird. It's amazing. It's amazing, I would say. But again, subtitles, you guys know that you can change the subtitles to any language you want, even Finnish, if that's what you want. German, no problem. Have you tried? It works well. I mean, that is it's not as good as English, but it's understandable. For sure, it's understandable. You know that there's a big debate going on in the Finnish universities whether or not we should uh, stop teaching in Finnish language and have everything in English. And of course, there are people that are very heavily against it. It's just that there is a practicality related to discussion, and the practicality is that if we explaining this material that I'm doing today two times, one for Finnish class, another one for English class, it's gonna be double amount of work to me. So to kind of like define the energy minimum would be the good way to just explain in English, and then the subtitles, use whatever language you prefer, and it's okay. Hmm. Yeah, this is what I don't know if it is really against the law, but at least this is something that because of this personal, we are not allowed to give any information about you guys to outside sources. Our private videos. Okay, this is a little bit against my vision because my vision is to be a messenger about this happy message about multi-body system dynamics to the entire planet, not to you guys only, but the entire planet. And the being a messenger, I think it's important. It's important. Yeah, yeah. Okay, what is that they commenting? Yeah, but you can log in and say that, because my name in the YouTube is a Professor X. I'm not using my own name. So you can figure out any name you want. In Teams, there it's your real name. I think it is your real name. Okay, anyways, so today is not a great day. We're gonna take a look at this bit more in the details next week. Okay, then I have a short story. I gonna just spend a few minutes to explain this to you. Okay, this story is such that these flexible bodies and the reference motion. Let's let me get started again. Remember when I was introducing the floating frame reference formulation, I said that this is a combination of two methods, finite element method and multi-body system dynamics. As it is, you can make this is the right kind of the way to introduce the method. Now these two methods, finite element method and multi-body system dynamics, can be coupled one way or another. This flexible description need to be described or need to be coupled one way or another. There is a one possibility that you do the coupling using your stiffness matrix. In a floating frame reference formulation, the coupling is made by using inertia description, mass matrix, and quadratic velocity vector, meaning that these components that are associated to inertia, they can look very bad because the coupling terms are located to this part of the equation of motion. By making another kind of selection, coupling could be introduced in a stiffness matrix. And when doing so, then the stiffness matrix is going to look very bad. So it's going to be very ugly looking. It's going to be messy, complicated. But typically in the floating frame reference formulation, not typically, but always in the floating frame reference formulation, the coupling is mass matrix. Now here comes the story. The mass invariants are the components that defines how tight is the connection. This is kind of weird, but most of the commercial software, they give you an opportunity to define, is this coupling to be fully coupled, partly coupled, loose coupled, no coupling. And I understand that these are two extremes, no coupling, full coupling comes with the clear benefits because no coupling, then you can run your system as a rigid bodies. You can check how well it works. You can see if the constraints are correctly made, so on and so forth. Full coupling will be that, okay, now you have the full capabilities to see how it performs. Everything that is between is a little bit unclear, but they are made for you, available for users because if it is full coupled, usually it slows down your computing quite a bit. Anything between here enhance the computational efficiency. And that's why the user can actually play with these coupling terms. These coupling terms are called mass invariants, and they come from the expression of inertia forces, inertia components that are mass and quadratic velocity vector. But most particularly, what is important is the mass matrix. And it all gets started from this kinematic equation, the kinematic equation that is displayed in my slides. So I have here the deformation U bar F that we describe by using finite element method. And when you're using this notation, and when you're deriving your elastic forces based on that, then something that appears along the development is mass invariance. Okay, this is the kinematic notation when you're using modal decrease of freedom, and your variables are listed here. They have reference motion and the deformation. And then once you're using this information and you advance in your definitions and in your computing, you can compute velocity, and you can compute acceleration. They all gonna look very, very bad. So they're gonna look very nasty because of this deformation. And then now we actually have this something we didn't have in the case of rigid bodies, and that's Coriolis acceleration. Because now it actually comes into play because if you have a beam-like structure like this, in this rotating coordinate system, there is a possible that particle is moving with respect to rotating coordinate system. And that's the definition of Coriolis acceleration. That happens in deformable bodies. Now, these are the components of acceleration. And once you submit all these to expression of virtual work for inertial forces, what becomes the built-to equation is a mass matrix. A mass matrix is enormous mass, big mass, very big mass. But some of the components in a mass matrix you can compute in advance. And the ones you can compute in advance are called these mass invariants. And the mass invariants are associated to these 6 components of the mass matrix, and they are denoted as a I1 to I9. And this is how you compute them. The weird part of this story is this. Now, the user can define which one of these mass invariants are part of the computing and which ones are not. And again, you keep all them part of the computing, you will get absolutely full coupling correct solutions, but very slow computing. You give none of them in a play, you get rigid body motion, which is very efficient. You get some of them in a play, you get something that is unclear. My recommendation, and this is how the display, or this is how this is a user interface in Atom software. You see that you can click, put this on and off as you please. My recommendation, don't play, because this is like playing with the fire. You can easily burn your face. Don't do that. Okay, that's it. Now one more story, and then we're gonna close today. So I see that I mentioned to Mustafa that in 10 minutes time, we're gonna close this thing. Okay, stress analysis. Stress analysis based on multi-body system dynamics. This is something that is a very important post-processing procedure, something that actually comes with the big value. So being able to define how is the stress history is in different location of your structure, that's something that you can use to define many important things, not just the static dimensioning of your structure, but something that is more fatigue related. And the fatigue is important. You know that the current trend is this, that there is a companies are looking more and more opportunities to use high strength steel, because high strength steel makes it possible to design more slender structures that are more lightweight. And the weight is important, because if you have a lightweight structure, you're using less material. Less material, as a rule of thumb. This is not exactly the case, but as a rule of thumb, you can measure the expenses based on the weight of your structure. So if it is very heavy, it's probably more expensive than lightweight structure. And the lightweight comes with the many other benefits, including the fact that if you, for example, build a mobile machinery as lightweight as possible, your energy consumption goes down. Your damage you're introducing to nature, if you have a, let's say, forest structure, will be less. And you kind of must do it, because there's another trend that is against this lightweight design. Another trend that is against that is electrifying heavy machinery. You know that there is more and more ways that people looking that hydraulics is replaced by electric drives, even in a mobile machinery, which is difficult. And it's difficult because the power density in electric motors is much lower than it is in hydraulics. That means that same physical space, same physical dimension, in hydraulics you can produce more forces. That's what it means. So they are like muscles that are stronger than in any other actuators. Anyways, so this is a big trend. These electrical drives are heavier. They need to find another way to reduce the weight, and the high strength steel is the one way to go. Now the problem related to high strength steel is that still the most economical way to combine the components is by welding. You know that. If you think about any other ways to combine the components, it's going to be expensive. Welding is affordable, but the welding comes with the problems because once you introduce the welding process, the welding imperfection that are typically located somewhere in a welded toy will act as an initial crack. So it's an okay assumption to say that once I have a brand new structure that comes out of the factory, it's already have a initial cracks. Then in a welded structure, is always a battle about the crack growing, not crack initiation, which is a big difference. Non-welded structures, if it is the crack is initiated, then that's it. You can throw the component away. But in a welded structure, it's always a battle about how much the crack is growing during the operation. And then comes the big problem, the biggest problem associated to welded structures, and that's the high residual stresses. So when you introduce the welding process, you're introducing a lot of heat to this particular part very locally, very locally. So it's not going to destroy anything except this particular local component or local detail. But now because of the residual strains, wherever you start loading your structure very locally, there's going to be plastic deformation. And exactly where the initial crack is located at. Very bad combination. So how much it helps if we're going to change to use a high strength steel instead of conventional steel? It's going to make things worse. Why? Because the residual stress is always going to be at the point that this linear strain stress curve is moving to be nonlinear. So it's always that high. So always when you are loading your structure, the crack started to grow there. And now when you have a slender structure, the dynamic loading is more significant. So it's even bigger problem than it was when using conventional steel. So those are the trends. All right. Okay. So how is it we can get these stresses out? So we have two possibilities. And one is a no good possibility, but still is a possibility. So what we can do is that we can use a real processing procedure, taking all the forces, including inertial forces, from our multi-body software and transport those to finite element software, pretty much where the original finite element model was located at, and then using a lot of pre-processing. This time it's not going to be pre-processing in a finite element method, but the loading cases, as many as a time step in your multi-body model to figure out the deformation again, not a degrees of freedom again. You already have this information once, but now you do it again. This is one possibility. Another possibility is that you're using the properties that are related to your elements to compute strains and stresses directly using your model coordinates. Very sophisticated, very nice, but not necessarily always available because it needs the synchronization between the different software. So that could be a bit of the problem. Okay, so these are the two ways. So this is the first way is this. You have your structure, you analyze it using your multi-body system dynamics, you get the solution, I don't know how many different time step you're using, 1,000, 10,000, 100,000. You're creating the load cases based on each of these time step. You're exporting them to a finite element model, and then you keep on solving them. Possible, very inconvenient. And you can easily make a mistake here too, because in a finite element model, you must have a boundary condition. It's not going to be in a balance if you say that here are my forces, my dynamic forces, they're in a dynamic equilibrium. So compute the deformation. That's not going to work out in a finite element modeling, but you need to introduce some boundary conditions. And these boundary conditions may be fighting against the deformation, introducing artificial strains and displacement and strains and stresses, which is going to be completely incorrect way to go. But theoretically, this is one possibility. And again, it could be the same model that you're using to extract this information you need to describe the deformation. That's possible, but this doesn't make much of a difference. Better way is this, you know, unknowns when you have the floating frame reference formulation is modal coordinates. Modal coordinates are associated to your nodal coordinates with help of this deformation matrix. So let's go back to the nodal coordinates. The nodal coordinates, like we learned in the finite element model, are connected to strains via kinematic matrix. This kinematic matrix is associated to each of the elements. So we can identify each of the elements here using the kinematic matrix, which is a matrix P here. You can get strains. And then you have, when you have a matrix of elastic coefficients, you can get the stresses. This is it. Combining everything, the one package, it's called modal stress matrix. This guy here automatically gives you the access to stress histories within multi-body system dynamics. So that's an alternative. All right, here are the drawbacks, positive things. So the first option, this whole exporting business needs a lot of manual work. You need to be super careful with that. Boundary condition, you must define them. Typically, extremely hard to do it correctly. And you solving your displacement twice makes no sense. Another one, efficient, but it's not necessarily always available. But wherever available, please use the option number 2. Okay, just, the next story would be fatigue. And exactly like I explained, the fatigue, to do the fatigue analysis. I don't know if you've been in a fatigue course already. No. Okay, so you've been in a fatigue course. So you correct me if I say something funny. So the fatigue in fatigue analysis is different depending if you look at the welded structures or non-welded structures. They're conceptually very different. So not much relation, because non-welded structures is all about the crack initiation. And if you see, like if you put your car engine in a part and you see that in my connection rod, I have a visible crack, better replace it, because then the lifetime left is not much. Whereas in the welded structures, like I say, is all about the controlling the crack growing. So that's what it is. All right. So fatigue is a statistical thing. So even though that we get the clear number out from it, it's still with a certain probability. And we cannot say that, okay, when this amount of hours is done, your system is absolutely failing. It's not going to happen like that. But we can say statistically, this and that amount of structures will introduce or will have a damage after this and that amount of hours. There's a statistical thing that the things are statistically distributed. Load connection. Loading is the most harder to get, definitely the most harder to get. And the crack, this is the situation. You're welding two plates together. This is a crack toe. And because of the imperfection in the fatigue process, this is where you can make a fair assumption that the initial crack is located at. And then this thing I mentioned about the stresses. Okay, shortly gonna show to you. This is the graph that you learn at the first year in your bachelor studies. So this is a stress. This is a strain. Stress strain. Still, material behaves in a way that is a linear until it's not. Okay, so the linear phase is something that you're loading your structure somewhere along this line. The deformation comes back and you go exactly the same form that you started, like this stick. I do this deformation. This is a linear deformation. I don't want to show how the nonlinear is, but the nonlinear means that you go the nonlinear phase. You take your loading off. You're no longer coming back where you started, but you're coming back the deformed form, meaning that your structure is bended, which is not great. So that's not going to be looking good. So typically the machines are operated in this section. Now, like I said, the problem in the welded structure is that very locally, because of the welding process, the stresses, again, super locally, are located here at the corner where the linear is moving to be nonlinear, always. Now, when you start loading, meaning that you can introduce strains a little bit away from this point, you're going to automatically move the plastic zone locally. And that's where the crack is growing. So that one more problem related to this thing is that there is a geometrical nonlinearity too, typically increasing the stress rate locally. Very local thing. that's the crack is growing. Okay. All right. I'm gonna. The boss is here. So so again, a full lecture in terms of technical quality. What should I do then to fix this thing? I need to play with my OBS. Yeah, yeah. Sorry, of course we're gonna do that, and that's where we're gonna close right after this. So the quiz is this. Oh, yeah, because of the restarting, I need to log in again. So what do you guys think? The success rate? Yeah, we'll do it that momentarily. Hold on. This is going wrong. So something is going wrong here. Finish activity. Teach. There is what? Yeah. Okay. What about this? Should be LUT2. LUT2. Okay. So again, this is all about the OBS settings. Alexander. Hmm. But he was using his own computer, own OBS, but with my settings, of course. I mean, my account, my account. Yeah, so weird. How many answers we have? Two. Okay, so we are so there's none of his the technical thing is willing to cooperate with me. None. Okay, so we get back to this next week. But how come you make a distribution like this if you get two answers? Yeah, this is not possible. This is something is wrong here too. Okay, today none of the stuff is working. Next week, hopefully everything is working. Okay, but let me ask you this. Uh, we have the visiting professor from Delft University, and he specialized in bicycle dynamics. Very unique dynamics, but he's using multi-body system dynamics in his studies. So would you like to hear, let's say, half the lecture about his bicycle dynamics? Okay, he's a guy that he's cooperating with some of the Tour de France teams, and so really high-end cycling. I mean, that the studies he's doing is not really super fantastic bikes, but they're doing also something with the pro athletic. Yeah. Okay. So let's do it in a way that half and half, because there are other stories, still a few stories that I would like to tell to you. One is included to contact description, biomechanics, stuff like that. Okay. But today, not a good hair day. Hopefully the next week is better. So I'm gonna close this streaming. Oh, what's going on now here? I'll see you guys next week.